Welcome to deepmentor AI. Today, we're diving into a topic that honestly sounds like science fiction, but is very, very real: quantum computing. Now, if you're a UPSC aspirant, this isn't just a cool piece of tech to know about. It's becoming essential. So we're going to tackle this from two angles. First, we'll get you the solid, core concepts you need to nail any question in prelims. Then, we'll build on that foundation to give you the analytical depth you need to write a killer mains answer. All right, let's just jump right in with a thought experiment. Imagine you have a database with 1 trillion, that's a 1 with 12 zeros, items. Think of it like a digital haystack, and your job is to find one specific needle. A normal computer would, on average, have to check about 500 billion items. But what if you could find that needle in just 1 million steps? Sounds impossible, right? Well, that's not science fiction. That's the mathematical reality that quantum computing brings to the table. Now, you've probably heard the elevator pitch for quantum computing. It usually goes something like this. It's a really appealing image, isn't it? A machine that just blitzes through every single possibility at the exact same time. But, and this is a big but, that's a bit of a myth. It's a simplification that actually hides the real genius of how these machines work. Okay, this table breaks down the difference beautifully. Your classical computer, it just guesses and checks. We call its efficiency O of n, which is just a fancy way of saying the search time grows in a straight line with the size of the haystack. For our trillion items, that's a mind-numbing 500 billion steps. Now look at the quantum side. Using something called Grover's algorithm, the efficiency is O of square root n, the square root of n. And that's the magic trick that takes you from 500 billion steps all the way down to just 1 million. For your prelims, that O of square root n quadratic speedup is a golden nugget of information. It's a massive leap for sure, but notice, it's not instantaneous. So if it's not just checking everything at once, like some super-powered parallel processor, what is actually going on under the hood? How does it pull off this incredible trick? Well, to get that, we have to go right down to the fundamental atom of computing, the thing that holds the information. On the left, you've got your good old classical bit. Simple, reliable. It can be a 0 or it can be a 1. That's it. But on the right, that's a qubit. And the qubit, well, it plays by a completely different set of rules. A qubit can be a 0, it can be a 1, or, and this is the key, it can be a combination of both at the very same time. It's living in a world of probabilities until the second you look at it. And this single ability to hold so much more information is the very first step towards quantum power. So, how does this weirdness of the qubit actually help us compute anything? Well, it all comes down to 4 basic principles. You can think of these as the fundamental rules of the quantum world. For the prelims exam, knowing what each of these means is non-negotiable. First up, superposition. This is that superpower we just talked about. It's the idea that a qubit isn't just stuck at 0 or 1, it can exist in a rich, complex mixture of both states at once. This ability to be in multiple states simultaneously is what creates this unbelievably vast computational space for quantum algorithms to play in. Next, we have entanglement, and this is where things get, frankly, a little spooky. You can take 2 or more qubits and link them together in a special way. Once they're entangled, their fates are intertwined. If you measure one, you instantly know the state of the other, even if it's on the other side of the universe. It's a mysterious, powerful connection that lets quantum computers handle complex relationships that would choke a classical machine. Now, this third principle, interference, is arguably the most important one. This is the engine of quantum computing. If superposition opens up all the possibilities, interference is what finds the answer. Because qubits have wave-like properties, their probabilities can add up or cancel each other out. A quantum algorithm is designed to cleverly amplify the waves of the correct answers and completely flatten the waves of the wrong ones. It's how the computer guides itself to the solution. And finally, we have to talk about the villain of the story, decoherence. This is the great enemy of quantum computing. That delicate quantum state of a qubit is incredibly fragile. The slightest little disturbance from the outside world, a tiny vibration, a bit of heat, can cause it to lose all its quantum magic and just collapse into a boring old classical bit. Fighting decoherence is why we get errors, and it's the biggest engineering mountain we still have to climb. Okay, so we've got the basic vocabulary down for prelims. Now let's put it all together and think about this from a mains perspective. How do these 4 principles actually work together to solve a problem? This is where we get into the how and why. Let's look at that search problem again, but this time step by step.
First, you put all your qubits into an equal superposition. At this point, every single possible answer in that huge database has the same tiny probability. Next, a special operation called an oracle finds the right answer and marks it, not by reading it, but by flipping the sign of its amplitude. The probability hasn't changed. Yet. The real magic happens in step 3, amplify. Another operation is performed that basically boosts the amplitude of that one marked answer while shrinking all the others. And you just repeat this mark and amplify dance about square root of n times. And with each step, the probability of the correct answer gets pushed higher and higher, almost to 100%.
And there it is. That's the core idea you need for a deep analytical answer. A quantum computer doesn't get its speed by brute forcing every solution at once. It gets its power from a far more elegant process. It uses quantum interference to systematically amplify the signal of the right answer, while all the wrong answers cancel each other out into silence. That's the real secret sauce. So what's the big deal? What can we actually do with this kind of power? For a well-rounded analysis, you have to understand both the incredible promise of this technology and the very real dangers and challenges it presents. The potential applications are just staggering. Think about drug discovery, being able to perfectly simulate a molecule to create life-saving medicines, or material science, designing brand new materials for super-efficient batteries or clean energy. It could untangle the most complex optimization problems in finance and logistics. But there's a flip side. With algorithms like Shor's, a powerful quantum computer could break most of the encryption we rely on today, posing a huge threat to national security and global finance. But let's be clear, we are not there yet. The hurdles are massive. That villain, decoherence, is constantly destroying our calculations. That means we have high error rates, and building reliable error correction is an unbelievably hard problem. Just physically scaling up to have lots of high-quality, stable qubits is a huge engineering feat. Plus, many of these machines need to be kept colder than deep space. That's why you'll hear experts say we're in the NISQ era. That stands for Noisy Intermediate Scale Quantum. The computers are real and they're powerful, but they're still very noisy and imperfect. I love this quote from the researcher Scott Aronson because it makes the whole process feel so real. It's not like pressing enter and getting an answer. It's a tense, high-stakes game of probability. You run the algorithm, building up the chances of getting it right. But when do you stop and take a look? If you measure too early, you get garbage. If you wait too long, decoherence might wipe out your calculation completely. It's a calculated gamble every single time. And this brings us right back to you, because this technology isn't just about physics and computer science. It's about policy, it's about security, it's about governance. As the future leaders and policymakers of this country, the challenges of the quantum era will land squarely on your desk. So the real question is, how will you prepare? How will you navigate a world where this technology can reshape everything, harnessing its incredible benefits while protecting the nation from its profound risks? That's the challenge that awaits you.